In this video, we will review parametrization, vector functions, and planes, all tied into this example. So there are going to be multiple parts of this example that we'll do, but they'll touch on these different topics. So here is the first part. Let's parameterize the intersection of x equals y with x squared plus y squared plus 3z squared equals 5. So first, pause the video for about 2 minutes to try this on your own first. So 4, 3, 2, 1, pause the video. Pause the video for about 2 minutes to try this. Alright, so hopefully you've done that. Hopefully you paused it for about 2 minutes to try this on your own first. If not, go ahead and do so now. So let's go ahead and start to talk about it together now. So when a problem talks about the intersection of two surfaces, we can remember our key idea for how we found intersections of curves in algebra. And one of the ways that we dealt with that was we isolated for a variable in one of the equations. And then the general strategy was we could try to then substitute one equation into the other. So if we can isolate for a variable in one of the equations, then we can substitute that into the other. So in this case, we already know what x equals in this first equation. So let's plug that into the second equation. So instead of writing x squared, we will have y squared because x equals y. And then we'll have plus the other y squared and plus 3z squared equals 5. And simplifying this, y squared plus y squared is 2y squared. So we get 2y squared plus 3z squared equals 5. So at this point, we see that this is an ellipse. So we are trying to parameterize this ellipse here. Okay, so one thing that'll help is if we divide both sides by 5, we'll get 2y squared over 5 plus 3z squared over 5 equals 1. Because once that equals 1, it's a lot easier to see what part of this will let be the cosine squared term and what part of it will let be the sine squared term. So we're going to let cosine squared t, and it technically doesn't matter which of these fractions I choose because it didn't specify what direction my parameterization had to go in or anything. So I'm going to let cosine squared t be the 2y squared over 5. And I'm also going to let sine squared t be the second fraction. It'll be 3z squared over 5. And the reason why I'm doing that is because that'll give me cosine squared plus sine squared equals 1. And that's an equation that we know is true. Okay, so in this first equation, if we square root both sides, we get cosine t equals square root of 2 over 5 times y on the right-hand side. If you notice I'm forgetting something, that's good. I'll come and comment on that. Okay, but for the time being, if I isolate the y, we get y equals root 5 over 2 times cosine t. Okay, so I mentioned I was sort of forgetting something. So what I was forgetting was a plus or minus. So if we wanted to here, we could have also used cosine of t equals negative root 2 over 5y, if we had wanted to. We have the choice. That would just give us a different parameterization, but that's fine. Alright, so if we do the same thing with the second equation, I'm going to skip some of the steps, and I'm just going to say what we end up getting at the end. Once we isolate for z ends up being root 5 over 3 sine t. And I get the same thing in terms of the plus or minus. So if I wanted to choose the negative version, that would have been fine. So with this setup here, because my shape was an ellipse, we need our value of t, based on the types of functions we're getting, cosine t and the sine t, to be in between 0 to 2 pi, that's going to be our interval, to go around the ellipse fully. Okay, so we know what y equals, we know what z equals. we just need to say what x equals. So then, well, at the start, the problem told us that x and y were the same. X equals y, which was root 5 over 2 cosine t. All right, so we are ready to write down our parameterization now. So I'm going to call this P-A-R'(n), just for short, to abbreviate parameterization. So we say what x is, it's root 5 over 2 cosine t. What y is root 5 over 2 cosine t as well. And what z is root 5 over 3 sine t. Okay, and then I state my interval. And my interval is 0 is less than or equal to t is less than or equal to 2 pi. And that is our parameterization right there. So let's box that. All right, so that was it for part A of this question, getting this intersection parameterized. All right, so let's move on to part B. Part B is asking the points 0, 0, root 5 over 3 and root 5 over 2, root 5 over 2, 0. Break the curve into two pieces. Set up an integral for the length of the shorter piece. Okay, so for this part, pause the video for about 3 minutes to try this one. 4, 3, 2, 1, pause the video. Pause the video for 3 minutes to try this one. I think this part is a little bit less standard. It's a little bit, it'll require more thought, most likely, on how to begin this one. All right, so hopefully you've done that. Hopefully you've paused the video for about 3 minutes to really try this question. Okay, so let's talk about how we'd begin. So we have a parameterization for the path. We need to know the times at which we reach these points. Okay, so I'm going to circle this first point. And I'm going to use what x and y and z equal to determine what time we reach this point at. So for example, I know that the x value is root 5 over 2 cosine t. And that needs to be equal to the x coordinate of this point. It needs to be equal to 0. All right, so similarly, the y coordinates need to be the same. So the y coordinate in the general equation is root 5 over 2 cosine t. And the y value of the point is also 0. So actually, I didn't really need to write that. It's the same equation as the first one. But okay, that's fine. It doesn't hurt to write it one more time. And then setting the z's equal, we get root 5 over 3 sine t needs to be equal to root 5 over 3. So if we think about what value of t satisfies this, what value of t in between 0 and 2 pi makes this true, it's just t equals pi over 2. Okay, so that's the time when we're at this first point that's given to us. Now let's do the second point. So for the second point, we're going to do the same idea. We'll set the x coordinate, which is root 5 over 2 cosine t, equal to this x coordinate, which is root 5 over 2. Let's skip the y coordinates because the y coordinates are exactly the same as the x's. So that doesn't really help for me to write them. Let's go straight to the z's. So the y's I won't write. The z's give me root 5 over 3 sine t is equal to 0. All right, so what's going to satisfy this is if cosine of t is 1 and sine of t is 0. And what makes that true is if t equals 0 and 2 pi. So there's actually 2 times where this occurs. All right, so now I'm going to try to draw a rough sketch of the curve so we can visualize what's going on here a bit. Okay, so we actually don't need to know exactly what this parabola looks like. Sorry, actually, no, it was an ellipse. Exactly what this ellipse looks like in 3D space. So I'm just going to draw like a rough picture of just, you know, it might be a slanted ellipse or something even. So when t equals 0 and when it equals 2 pi, we're at the same point, root 5 over 2, root 5 over 2, comma 0. And that makes sense because we were trying to, the way we parameterized this was to go one full time around the ellipse. So our interval went from 0 to 2 pi. So it makes sense that we're back sort of at the starting point once we reach 2 pi. All right, and then at t equals pi over 2, just sort of using logic, if it takes me 2 pi to go around the full ellipse, by pi over 2, we'd be a quarter of the way around. So this question said we want the shorter piece. So the shorter piece is from this point to that other point. So in terms of the times I'm going to use, if we start off with t equals 0, and then we go until t equals pi over 2, that'll get it done for us. So this red thing, this is the shortest piece. So now we know the values that go at the top and the bottom of our interval. It's going to be 0 and pi over 2. All right, so we're ready to write down a formula for the arc length. So arc length is an integral. Now we know it goes from 0 to pi over 2. That's our starting and ending time. And it's a square root, a big square root of x prime of t squared plus y prime of t squared plus z prime of t squared dt. So if we take these appropriate derivatives, so we end up with this integral from 0 to pi over 2. So the derivative of x is negative root 5 over 2 sine t. That's the derivative of x. So then we square that. Y was the same as x, so it's going to have the same derivative. That's negative root 5 over 2 sine t. Square that. And then we have to take the derivative of z, which is root 5 over 3 cosine t. Square that. Okay, and then we put this dt on the outside. So this problem just said set up an integral for this length. And at this point we have that. So it just said to set up an integral. It didn't say that we have to evaluate it. So at this point we would be done. All right, so let's look at the next part of this example. All right, part C asks, find the unit tangent vectors at 0, 0, root 5 over 3. So pause the video one more time, this time for about 2 to 3 minutes, to try this question. 4, 3, 2, 1, pause the video. Pause it for about 2 to 3 minutes and really try this next part. All right, so hopefully you've done that. Hopefully you've paused the video to try this. So one thing that we're going to need to keep in mind was, what was the time at which we reached this point? And we said that this happened at pi over 2. That's when we reached this point. So let me draw a sketch so we can visualize this a little bit. So in this sketch, I'm going to draw some axes. In fact, our curve actually here is in 3D space. I won't even bother drawing axes. Let's just say I had something that went like this, and then it sort of curved around, and then it did something like this. So I had some curve, and let's just say that this exists in 3D space, and it looks something like that. And let's say that the point 0, 0, root 5 over 3 is somewhere here on the curve. So when we talk about a tangent vector, well, the tangent vector is kind of like a tangent line, except it's a vector. So we'd be talking about a vector that sort of points this way, so perfectly matching how steep sort of the direction of the graph right at that point. And the fact that it says it's a unit tangent vector means that we need the length to be equal to 1. So there are 2 unit tangent vectors. One is in the direction that I just drew, and the other one is in the exact opposite direction. That would also be a tangent vector, as long as I keep the same length. So these are both unit tangent vectors, this orange one and this green one. They're both unit tangent vectors. Okay, so let's begin this by first getting the tangent vector. All right, so let me put this in black. So the formula for the tangent vector So if we can write this as a position vector function, the tangent vector is r prime of t. It's the derivative of the position vector function. And the way you take the derivative of r is you form a vector in which you take the derivative of the x component, whatever x of t is in your parameterization, and then the derivative of y, and then the derivative of z, whatever their respective equations are. All right. So for this particular problem, we've already done these derivatives in the last part, in part b. The derivative of x is negative root 5 over 2 sine t. Same thing for the derivative of y. It's negative root 5 over 2 sine t. And the derivative of z was root 5 over 3 cosine t. Okay. So we needed the tangent vector at this time, at pi over 2. So now let's plug in the fact that t is supposed to be pi over 2. And if we do that, we end up getting that our tangent vector equals negative root 5 over 2, comma, negative root 5 over 2, comma, 0. Okay, so I'm going to call this vector t. T for tangent. Okay, but we're not done yet because it's not a unit vector necessarily. So let's make it a unit vector now. Make it a unit vector. So we can make it a unit vector by dividing it by its length. So we would get the vector t divided by its length, and that will give it a unit vector, make it a unit vector in the same direction. Okay, so this is 1 over the length of t. So to get the length of t, I take a big old square root. I take each of the entries of t. So I take the negative root 5 over 2. We square that, and then add it to the next entry squared, negative root 5 over 2 squared, add it to the next entry squared, so 0 squared. Okay, and then we multiply that by the vector t. So we multiply this by negative root 5 over 2, negative root 5 over 2, comma, 0. All right, so simplifying this, this fraction at the front becomes 1 over square root of 5. So I have that times negative root 5 over 2, comma, negative root 5 over 2, comma, 0. And then this 1 over root 5 is going to cancel these root 5s that are in the numerator. So we'll end up getting negative 1 over root 2, comma, negative 1 over root 2, comma, 0. Okay, so that is one of our tangent vectors. But there's another one. We said that the other one's in the opposite direction. So the other tangent, I should say unit tangent, the other unit tangent vector is negative 1 times this. So if we multiply this vector by negative 1, we get positive 1 over root 2, comma, positive 1 over root 2, comma, 0. So those are our two unit tangent vectors to this curve at this particular point. All right, so one more part to this example. Okay, so I mentioned at the start of this video that this example would tie in a bunch of different concepts. So far we've done parametrization, we've done arc length, we've done vector functions in part C and getting a tangent vector. And now in D, we're tying in planes. So one more time, pause the video for about 2 minutes this time and try this question. 4, 3, 2, 1, pause the video. Pause it for about 2 minutes to try part D. We're finding the equation of the plane that's normal to the point 0, 0, root 5 over 3. And I think I want to add one extra word in here. So what I want to add is normal to the curve. Normal to the curve at 0, 0, root 5 over 3. Okay, so now pause the video for about 2 minutes to try this. 4, 3, 2, 1, pause that video. Pause it and try this for about 2 minutes. That's likely not going to be enough time to finish the question, but that's okay. I don't care whether you can finish it in this amount of time. I care that you're thinking about what the key steps are, how you'd begin. All right, so let's start to talk about it together now. So if I want the equation of a plane, we need two things. We need to know a point that the plane goes through, or a point that's on the plane, and we need to know the normal vector to the plane. So the point is easy because it tells me the point. It says that the point is 0, 0, root 5 over 3. All right. So now we need a normal vector. And the idea behind it is the question says that the plane needs to be normal to the curve. So the plane itself needs to be sort of perpendicular to the curve right at this instant. All right, so if I go up to our general sort of arbitrary picture that I had up here of this curve and this point, and when we're drawing these sort of direction tangent vectors, I need my plane to be normal or perpendicular to these tangent vectors actually. So if I draw a picture, so if I draw, a vertical line, and I start to draw like a line this way to sort of represent, oh, it's a plane, maybe it's sort of going in a diagonal direction like this, and then I draw a line here to sort of really make a plane. These unit vectors need to be perpendicular to this plane. That's what it means for the curve to be normal to the plane. These tangent vectors right at that point need to be perpendicular to that plane. Okay, so the tangent vector is my unit vector here. The tangent vector to the curve, we want that to be our normal vector. Okay, so the normal vector here is, it is just, let me use the one without the negatives. I'll use the 1 over root 2, comma 1 over root 2, comma 0. Okay, in fact, any multiple of this is going to be a normal vector. So let's just make the algebra a little bit easier, and let's scale this. Let's scale by square root of 2 for nicer numbers. So if I multiply everything in this vector by root 2, we get 1, 1, 0. And all that does, all that multiplying this vector by root 2 does is it just stretches it. It just makes it longer. And that doesn't change its direction. It's still pointing in the same direction as it used to be, but it's just a little bit longer. So it's still going to be normal or perpendicular to our plane. All right, so we have a point, we have a normal vector. Now we're ready to write down the equation. So the equation of a plane looks like n dotted with the vector x minus x naught, comma y minus y naught, comma z minus z naught needs to be equal to 0. So if we plug in what we know, the normal vector is 1, 0, dotted with x minus the x coordinate is 0, comma y minus the y coordinate is 0, comma z minus, but the z coordinate is something else. It's root 5 over 3. That's okay, we can handle that. Close that vector bracket, and then this equals 0. So typically, the convention is when we write down the equation of a plane, we get it into the form after we evaluate the dot product. So now let's take the dot product of these two vectors. So we'll do 1 times the x is just x. Yeah, and then we'll get plus 1 times the y is just y. And then plus 0 times z minus 5 root 3. So let me write it out fully. 0 times z minus root 5 over 3. And this equals 0. And that's simple enough to simplify, so I will. We'll get x plus y equals 0. And this is the equation of my plane in standard form. All right, in the next video, we will do some more parametrization review questions.